Okay, so this is going to be a little bit more like our sort of more traditional MOPA talks in the sense that it's very much a work in progress. Um, so I'll sort of talk a little bit. These are ideas that I've kicked around with Roman over the last couple months, and that grew out of a paper we wrote together a couple of years ago now. So the paper we wrote a few years ago, we talked about was about what's called neutrally expandable models of arithmetic, and we introduced this notion of neutrality. So we talked about different notions of genericity that had been studied in the literature about models of PA. So you could sort of think about arithmetic forcing. You could think about Robinson forcing somehow in arithmetic, and Alf mentioned in one talk a few years ago, in I think in the workshop, some papers he did with Chris Miller and Charlie Steinhorn on generic expansional theories, and this work originated in a paper by Chatsidakis and Pillai, and so this notion of genericity is sort of loosely based on the Chaltidakis Pillai ideas, but not not necessarily like uh, a faithful translation, and that's sort of where today's talk comes in. But this was the notion suggested by Alf, which a set is neutral if it doesn't change the definable closure relation in the model. Right? So you look at sort of if B is definable from A using this predicate X, then B is actually just definable from A. And so if you actually sort of go in and look at the Chatsidakis Pillai paper and like literally write down what it would mean in the context of arithmetic, you would get this definition. There's slight differences from what they say, and moreover, what they're talking about is sort of expansions of theories. So rather than expansions of a model, but this is sort of the rough idea that essentially if you have a formula that sort of defines some tuple, then and it sort of defines a large enough set, then any pattern here, any sort of pattern in these one to n's will sort of appear as it will sort of show up in this X in some sense. Let me X out here. So right. So a simple scenario would be to just look at the order, like an ordering, and so you could look at something like less than xn as just this is your formula, right? And so it has no parameters, and so essentially this would say that X would have sort of there would be lots and lots of every possible pattern of picking out elements of this sequence that would show up in X would be there, right? And so it takes a second to sort of actually grok that definition, but it's sort of a what you might think of model theoretically as being not as being very sort of fuzzy, right? I guess the way Alf described it was you think of a model and then just a subset of that model that's just random, right? It's just fuzz on in that model, and it's sort of this is why we sort of defined it more precisely with this notion of not changing the definable closure, and that's sort of is supposed to capture this being very generic in the model. But I want to sort of see, is this actually the same notion? What is sort of, if we were going to be more precise about this translation, what exactly do we get from this definition? Okay. And when we studied neutrality, I made this comment I may have made the comment in our paper, or sort of proposed it as a question, where we sort of assumed that CP generics are going to be neutral. And so if it has this property, it does not change the definable closure relation. but if you actually go in and try and prove it, this definition is not very easy to work with in the context of PA. For all the sort of usual reasons that PA is model theoretically problematic. So we'll sort of talk a little bit about this, but before, let me just sort of say a little bit about neutrality first.
Sorry, Athar, but before you move on.
Yeah, go ahead.
This CP generic, is it clear? I think this is true. Are Cohen generics, are they CP generic? Is that true?
No.
Nope.
They're not going to be CP generic. So what I'm going to say is I'm going to say something about inductive set. So no inductive set is going to be CP generic. No cut is going to be CP generic. So lots of things that are very much not generic in the model theoretic sense, in the sense of like you learn something about the model in some sense by using a Cohen generic. So for example, there's a Simpson result, right? That you can use model theory. You can use a Cohen forcing to expand to a pointwise definable model of PA star, right?
But is the question about arithmetic Cohen generic? How about a set theoretic Cohen
set
generic?
theoretic.
I'm not quite sure what
I meant either, but I mean, yeah. I was thinking about arithmetic Cohen generics. But
arithmetic is out of the question because it's inductive. But what about?
Okay, so set theoretic.
I seem to recall that at some point we proved that in fact, yes, they are.
That Cohen generics are.
Yeah,
okay.
I think that's actually the case.
Okay, that's interesting,
it should be the case.
Okay.
Basically, you think about hitting all the generic sets. Well, that's going to cover all these CP conditions.
Yeah.
And so, it's not entirely surprising.
Yeah. Okay. That sounds reasonable.
Thank you.
Okay. So some basic results on neutrality that we worked through. Well, some of these are basic in the sense of actually being quite trivial, and some of these are not trivial at all. Of course, so neutrality is this notion, as I said at the beginning, of not changing definable closures. So prime models are, everything is neutral in a prime model. Any zero definable subset is not going to change definable closures. At one point, we thought that this third bullet was obvious. We thought that, in every model, the standard cut is neutral. We thought this was sort of an obvious statement, and we re-examined it, and it's true, but it actually is a corollary of a very much non-trivial result due to Canove. Moreover, we eventually realized that recursively saturated models have no undefinable neutral classes, and so this was sort of maybe not disappointing, but it was interesting. We kind of assumed that maybe there should be some way, and eventually we realized no, there's no sort of arithmetic forcing way of getting neutral subsets and things like that. And so for the rest of this talk, for the most part, we will assume recursive saturation, and we're going to sort of try and talk through some of these ideas in the context of CP generics. So first thing is okay, can omega be CP generic, right? So and hopefully not, because the standard cut is very much not generic in some sense, and it's sort of you just follow the definitions. It's very it's not hard to see that. And I go through a proof here, but it's really not anything. So I'm not going to spend too much time on this. I just wanted to sort of immediately see that this is this shows a separation between the two concepts, right? That we have an example of a set that is neutral, omega, but is not CP generic. Okay. So at one point when we were studying neutral subsets, we realized that okay, we want to not allow for, we don't want, we want to throw out all the cuts, and we really just wanted to study which ones, we wanted to throw out all the cuts, and eventually we sort of settled on really considering which classes can be neutral. And this is where we eventually figured out, this result on recursively saturated models not having neutral classes, or undefinable neutral classes. Okay, and so this is our next sort of result is about CP generics. A CP generic cannot be a class, and so this is not. This is also not hard, but it's maybe worth thinking through a little bit, just because. Well, actually, I think this proof is probably not necessarily worth going through too much either.
Why don't we go over it anyway?
Let's go over it briefly. Okay, so we start with a recursively saturated model. You take a CP generic, and so I'll sort of say what large enough means at some point. But so you have a recursive enumeration of all Skolem terms, and then you look for something that is not in the Skolem closure of this element of C, essentially. And that's what's going on here, right? This is, if this type is realized, right, if X realizes this type, then theta of XC holds, and X is not in the Skolem closure of C. Therefore, if X is CP generic, then you have you have something that is defined from theta of, from theta that is not in X. Right? This is immediate from the definition of genericity.
All right.
Okay. So all you really need here is that A is large enough so that this set XA is infinite. Okay.
Right. So it really matters. It's not just a cut, but no bounded set.
Yes. Well, hold on, let me go back to the mention of cuts. When I actually prove for cuts, my proof about cuts actually was very specific. I was very specifically thinking about cuts, right? Because I was trying to find 2 points. One is in the generic and one is not, and so it's not sort of closed downwards. But you could do a very similar argument to sort of show it has to go up, right? That there always has to be a bigger element that is sort of in the generic. This argument about classes, there's a couple subtleties here that I wrote down in a paper that's sort of in a draft somewhere. So if you're interested in those subtleties, you can ask me about it. But things like, well, could X be an omega sequence? And very, very quickly you see that it can't, right? And so, in other words, this set XA here that I underlined there has to be one of those that's infinite. And that's, once you have that, then you can get this. You can sort of get this type that's realized and all that. One of the things that's going to keep coming back. Well, one thing that's going to come up when I discuss some of the layer proofs is that some level, this definition really only makes sense in a model that it has some level of saturation, and so you could ask what, if you have a model, any model, what are its CP generics, what do they look like? But you can't do a lot without these sort of compactness type arguments and these, the actual paper by Chatzidaxis and Pillay makes extensive use of this notion of some notion of uniform finiteness, which I'm not going to get into, but you can imagine that PA very much does not have that, right? Ordered structures will not have that. And so you kind of have to play around with saturation and compactness to kind of almost cheat at getting some strong form of finiteness. These finiteness results. But that's all that to say is just to bring me to this particular lemma, which is the main lemma for my the result that I actually want to talk about. That any infinite definable set in a recursively saturated model has to intersect the CP generic, any CP generic, and the complement of a CP generic. Non-trivial, right? And this is again sort of this notion of finiteness is important, right? And when I say infinite, I mean externally infinite, right? So I'm not talking about in the sense of the model or anything like that. It's it could be a bounded set, but as long as it's a definable infinite set, it has to intersect the CP generic and it has to intersect the complement. Okay.
Isn't the complement of a CP generic set itself also CP generic? I mean, just by the definition?
I think that's by definition, yeah.
Okay.
Yeah. Alf, you can correct me if I'm wrong on that, but that looks to be.
It looks very symmetric.
Yeah. Okay, so this is our main lemma, that any definable infinite set intersects the CP generic and its complement. And so you sort of just again realize some type that says, well, X is not in the skull enclosure of the element that I use to define my set. Right. So I have some set. I need my pointer. Sorry about that. Right. Kick me out of this. I have the set is defined from this parameter B, and this says X is not in the skull enclosure of B. Okay. And okay, so it's this type is realized, and by genericity, there's something in X that must be there, and then similarly, there must be something not in X that must also be in something not in the generic that must be in this set A. Okay. Okay. So my main result that I've been sort of thinking about for the summer was when are CP generics neutral, and in particular, if you have a recursively saturated model on a CP generic, can you show that it must be neutral? Okay. Which showing that something is neutral is sort of saying that if you take a formula in this expanded language, can you somehow convert it that defines some element? Can you somehow convert it to a formula in the language of arithmetic? Right. So without the predicate, and so it's sort of without nice properties of so this notion of neutrality you could sort of talk about in other contexts besides arithmetic, and without nice QE type properties, model theoretic type properties, it is not necessarily the easiest thing to show that something is to sort of say you can eliminate this predicate from a definition. Okay. And so, instead of showing that it's neutral, I show essentially just that the definable elements coincide, and then the result pretty much follows just by sort of inspecting the definition of genericity. And right, so if something is generic in M, then it's also generic in the structure MA, where A is sort of a fixed constant in the structure, and so you get sort of, well, the definable elements of MA coincide with the definable elements of M, and all that, sort of all the normal stuff that you need to prove that that the definable closure relation doesn't change. Okay, so I sort of went back and forth on a few different kinds of inductions that I might be able to use to actually prove this result. And it ends up getting a little ugly, and so I'm really just going to show you a flavor of it. But excuse me. But essentially, you use induction on the quantifier depth of a formula that purportedly defines an undefinable element. Okay, and so really, rather than saying induction on the quantifier depth, I really should say induction on the number of bound variables that interact with the predicate x. Okay, so that's really what I'm going to try and do is if I have if I have a formula that defines a using n variables in terms interacting with this predicate, then somehow I want to reduce that to n-1 variables and somehow maybe increase the PA complexity of that formula. Okay. That's going to be the idea. I want to, I want to use the fact that I can increase the PA complexity as much as I want, as long as I'm decreasing the use of actually using that predicate. Okay. Right, and so this is so a formula that could define an element uniquely would look like some set of quantifiers and a PA part along with some terms on those bound variables plus the variable y that I'm using, that somehow, and those terms somehow interact with x in a predefined way. Okay. Okay. So this is just the sketch of the idea for the base case, rather than consider all cases where if you look at what I had on the last slide, I sort of have this PA part. I'm just kind of going to ignore that for now, and it's not going to change. It doesn't change the argument too much, but it just simplifies things for the purposes of the slide. And so you look at some particular sequence of terms that, and you sort of assume that A is the unique thing that maybe for some of these terms, T of A is an X, and for others, Ti of A is not. Right? And maybe A is the unique thing that has that particular pattern with those terms. And you want to show that, okay, if A is unique with that, then you would have that A is somehow unique. A has some sort of unique property in just the PA, in the arithmetic language, or something like that. Okay, and so for without loss of generality, you assume that each of these terms does not, each of these TIs is not a definable element. Otherwise, you could sort of just rewrite the formula to only reference those terms that are not in the skull enclosure. Essentially saying, so just think about the example where, okay, T of A is equal to 0. It does, let's say T0 of A is equal to 0. Okay, saying that 0 is an element of X is not really saying anything about the element A, right? And so it's you can rewrite the formula to not reference these sort of constant terms that are, you know, the definable elements. It's not going to.
But some non-constant terms have to remain.
Yes. Well, I mean, if none remain, then A is sort of the unique thing that sends, right? So again, A can't be the unique thing that such that T of A is equal to 0.
Right.
Right? Otherwise, A is definable, right? And so if you're starting with the assumption that A is not a definable element, right, okay, then you get that, okay, some of these non-constant terms have to.
Identity. You can always throw in identity.
Yeah, yeah. And you don't really, you really actually don't even need to throw in the identity, because just this assumption that A is not a definable element will throw out things like this from being the thing that is unique about A, right? A is not, if A is a unique element that the term T sends to 0, then that's a definable statement in the arithmetic language.
Okay.
And so you essentially so what do? We assume that none of those are actually definable elements, and we look at this formula that just asks what is, so this is going to be our A, what is Ti of A, and it sort of names each of them. Okay. And so if you follow the definition of CP-genericity, this is a formula in n+1 many variables with where each of those n+1 many variables is not a definable element, and therefore any pattern that you want to happen will happen, right? And so any pattern that I want to happen is, I want the pattern to happen where the xi's are in X if and only if the I is in I, and I want at least one thing that has a different, that is different from A. In other words, I want, if A is an X, I want xn+1 to not be an X, okay? And so in other words, by CP-genericity, there is something different that satisfies this formula, okay? And that contradicts the uniqueness of A. Okay. Before I move on, is this okay? Are there questions on this base case? How I'm actually removing the use of X here? Okay. Right. So in other words, each yeah, right. So in other words, you look at the two, right, you look at the two subsets of 1 to n+1. You look at the two subsets of this set that extend I. Right. So there's two of these that extend I, and one of these satisfies the pattern, and one of these A doesn't, and so you get something that's different. Mm-hmm. Yeah. Okay. So roughly the inductive step, I couldn't find a nicer, so there probably should be a nicer way to prove this than essentially brute forcing all the possible things that can happen. But after doing a few different special cases, I sort of boiled it down to the 4 options for the starting quantifier and the ending quantifier. And in every case, I want to remove that last quantifier. So rather than going through all of them, I'm really just going to go through these special cases that morally give you the idea of the proof. And again, you can try and decipher my notes if you are interested, and I'm happy to send them your way. They're still very much in draft form, so I'm happy to get comments and send them your way if you're interested in that. So there's sort of the 4 cases for Q1 and Q1, right? For all there exists for all, etc. Some of these cases sort of are, I'm going to cover the special cases where n equals 1 and n equals 2, because that really is where I got the idea to how I was able to generalize it, and the generalization is not much more complicated. Okay. So suppose that you have this formula for all x, T of AX is in X. Okay, and you're supposing that A is the unique element satisfying this. Okay, and so you want to somehow reduce the quantifier depth of this. So by the lemma, you can sort of see, well, the function defined by T of A right? The function that sends x to t of ax must have finite range. Right? Otherwise, if it had infinite range, then it would have some elements that it must intersect the complement of x. Right? And so this is the idea here, right? That so that it has finite range, and therefore you can enumerate those elements as sort of define the range of that function must be sort of a sequence of elements definable from A. And you can sort of write down like, right, F1 is the least element of the range of T of AX or something like that, right? And similarly what the others. Okay, and so moreover, for each I, these Fi's are elements of X, and so A is the unique element of M such that each X is going to be T of AX is going to be one of these F's of A, right? One of these Skolem terms, and each one of those is going to be an X. Right? And otherwise, you would say that otherwise A won't be unique, satisfying the original statement. Okay. And so this is what I mean by saying that we're trying to reduce the number of a number of variables interacting with terms in X. Right? And so, in other words, the only thing I'm going to say about X here is these things about Fi of A. Okay. And so, right, if you actually sort of if I actually wrote it out, you would sort of say something like this, that I of A is an X. And now that you have your PA part and your sort of reduced complexity X part, right? And then inductively, well, now I can sort of, I know what to do with formulas that that look like this. This is sort of the base case at that point. Okay. Again, this is very much a special case, but all of the patterns that look like the patterns that look like this are quite similar, right? And so you could think about, well, there could be more than one term, right? You could think about well, the conjunction of m different terms where T of AX, T1 of AX is an X and T2 of AX is not, and things like that. But you just this is the same idea for all of them. Okay. Okay. So the second special case, I want to actually go through this one as well. I'm probably not going to go through the others. Sorry. Oh. Okay. All right. So similarly, you could think, okay, if A is unique, satisfying that there is something in the range of the function T of A, given by T of A, in X, then that's saying that all of the other ones don't intersect X, right? For all W other than A, for all X, T of WX is not in X. And so again, you use a sort of finiteness lemma. That means that the range of the function T of WX must be finite. Okay. For each W not equal to A, the range of the function T of W dot must be finite. Okay. And so you write down this type that essentially asserts either W has either W sort of gives rise to a function that has infinite range, or there's something in its range that intersects X. Okay, or the range of that function intersects X, I guess. And so if you think through this, well, okay, I just said it can't have, no W different from A can have infinite range for this function, okay? And if A is unique, is a unique thing that intersects X, well, the second condition can't be true either. And so this type is not realized in this model. Okay. And so, okay, you might look at this and say, well, if you look carefully, you see that this is not a PA type, right? And so this is a type in the expanded language. And so my assumption in this theorem was actually that the expansion itself is recursively saturated. And I'm going to talk a little bit about that. Maybe I'll say a couple words on that later. But so most of these types will have to sort of use the predicate X, and we might, if we think a little bit harder, we might be able to get rid of that. But it's not so much of a problem for me right now. But sort of going back to what I said about uniform finiteness, this kind of I'm really using recursive saturation here to really as a I'm really just using compactness here. I just want to get a finite set of functions that actually tell me everything in the range of these functions, right? And so this type is not realized, and so you find some m so that for each w, the range of t of w is contained in this set. And so the range of t of w for each x t of wx is 1 of f1 up to fm of w. And then you can say you can say this statement about a more concisely by saying either the function t of a is not contained in these finitely many functions about a, and this is sort of this is sort of my nod to uniform finiteness here, that somehow either the range of this function is too large, or everything in that range is in X. Okay, and so now I'm defining A as this unique thing. I'm defining A as this unique thing with these properties, but now I'm not. I don't have any quantifiers over the portion that interacts with X at all, right, with the predicate. Okay. The other cases are very similar, but are very similar in the sense of essentially what I'm trying to do. I'm trying to reduce this quantifier. I'm trying to sort of get rid of one quantifier, and eventually I do that, right? And so I'm not gonna run through those right now, but I can back up and talk about them if it's worth saying anything. But it's sort of, this is the general pattern with this result, is that that each what's the best way of saying, each for each case, I'm looking for a particular type that I actually don't want to realize, right? Using sort of I want to write down this type that cannot be realized, otherwise it would contradict the uniqueness of A in some sense. Okay, and then once you've said that, written down this type, and you say that it's not realized, then you get a finite set of functions to deal with, or a finite sort of you get to do some of these uniform finiteness tricks that were done in the original papers, and that's the main idea in each of these. I'm trying to think if there was anything worth saying on this example. Such a witness. Right. Okay. So again, in these two examples, there's nothing much to say other than just to say that each of these I'm dealing with one particular case. You can talk through the different patterns that could appear with more than one term and all that. But the main thing is each one of these, whenever you see X in the statement, in this sort of statement in the middle there, it's actually there's only one bound variable in those terms, right? And so, but inductively, I can get rid of all of them. Okay, so inductively, I can sort of eventually say something about A that is in without any of those terms. Okay. So yeah, just those were those special cases. The general cases are very, very similar, and so there's you sort of run through this by just taking away one quantifier, and possibly, usually what ends up happening is usually what ends up happening is by when you go from this PA part to this PA part, right, from this PA formula to this theta, this theta is sort of going to be more complex, but then going from the I guess I should have used a different color there, but going from the TIs to the FIs, we use fewer variables, and that's what the star is supposed to represent. The asterisk is supposed to represent using the variables x1 up to xn minus 1. Okay. And the J could somehow be some, a different set of terms, right? You might have a lot more terms down here than you had up there, right? So, there's no, these might be quite different. Okay. All of these things had to be done somewhat carefully to sort of say, well, let me just leave it at that. You do this carefully enough, and you sort of you can, if you do this carefully enough, you can sort of find this theta that makes this formula that somehow is complex enough to make this formula sort of not necessarily equivalent, but also define A uniquely. Okay. So I'll leave it at that. I rushed through this because a lot of the results are actually quite technical, and so I mean, meaning those special cases I skipped through are really technical. I'm happy to walk through those in a more slow and actually sort of in a more slow way, but if there's interest, but I'm happy to end it here as well. The main things that I'm still thinking about and I'd love input on is this first question was suggested by Roman. Do we have this notion of a generic elementary submodel? And so I showed that there are no generic cuts, and so do we have a notion of a generic elementary submodel? And I have not made any progress on that. The second question is, I really want to, the statement that I wanted to prove is that if M is recursively saturated and X is CP generic, then X is neutral. That's what I want to prove. And what I actually proved is if the expansion is recursively saturated. And I don't think that's a problem for probably reasons that are obvious, but I didn't spend enough time to actually ensure that, well, given a recursively saturated model and a CP generic subset, that it does have a recursively saturated elementary extension that is CP generic, a recursively saturated in this expanded language that is CP generic. That should follow from sort of that should follow, but it's not. I originally thought that it was more obvious than I think now. Right? And so now I'm going to actually slow down and actually look at that a little bit. What I can say here is that, of course, this question, if I have a model and any subset, well, if that set itself is not CP generic, then there's no hope. The failure of genericity will extend, and there's nothing you can do. But right, so but if you start with a recursively saturated model and you have a CP generic subset, is it necessarily the case? Is it always the case? Right? Is it always going to be that every elementary extension is CP generic? If not, what more do we need to sort of say that that's always going to happen? And things like that. So there's a bunch of questions I'm thinking about around this idea of extending generics in some sense. Okay, so I'll end here. I know I spoke way too fast, but I'm happy to go back and slow down on some things if anyone is interested. Thanks.
All right, thank you. Athar, there may be other questions, but how about, so what is known about the existence of CP generics?
It's sort of, if you just like write down all the conditions that are needed. So I actually did this as an exercise. I don't think it's really particularly exciting, but if you write down all the conditions that are needed, you take a countable model, it will have a CP generic subset.
Any countable model?
Any countable model, because essentially what you're saying. I actually wrote this down. You kind of like you enumerate its definable subsets and you sort of meet and avoid them as you need.
Oh, I see.
So in other words, you keep track of the things that you want to be in the generic and the things that you want to be in the complement of the generic, and then you build it up.
So existence is not problematic. It's just a question what those what those sets that you construct really look like. What
Yes.
structures you can get.
So I guess the thing with existence that could be interesting is can you do it in a way that makes the expansion saturated?
Mm-hmm.
That's what I want to do, because I want to get this theorem.
Yeah.
I want to change this theorem to I want to change that mx to just m, right? And so if I can start with a recursively saturated model and then expand it to a recursively saturated expansion that is where the subset is CP generic, that I have not. I shouldn't say that it's hard. I should just say I have not thought through it. Right. So it's probably obvious, and I just didn't think about it enough.
Right, and it also seems that in this theorem you do not need M to be countable. You just need enough saturation.
I didn't actually use countability anywhere. In my notes, the only time I actually used countability was when I wanted to show that they exist. Right. So I don't think I use countability in any of these.
So is it easy to show examples of uncountable models without CP generics? Or
I would have to. I think I don't know if that's easy.
It would be nice to know what kind of obstacle is there.
Yeah, at this point, the only obstacle is just that it's obvious in the countable case, right? And so it's obvious what to do in the countable case, right? You enumerate all the definable subsets, and then you meet and avoid them as you need.
And you cannot go beyond omega in the construction?
Well, I just haven't thought enough about it, because you might run into some set theoretic things I didn't want to think about, right? So I'm sure that it's probably true, right? It's probably, there probably is always a CP generic for any.
No, that would be boring.
Yeah,
It should be the case that any model has one.
It should be the case, because
that's what you're saying, Al?
Yeah, it should be the case that anyone has one. There shouldn't be any obstructions.
It should be like,
It's very, very hard to cook up a theory which doesn't have one.
Yes.
A model which don't have one.
Yeah. It's basically like.
Can be done, but.
Yeah, it's basically just you take a bunch of random points in the model, right? It's really stupid, right?
Basically, it's a forcing construction, right? You're just basically building a generic.
Yeah. I guess it really feels like a forcing construction. So, yeah.
Which leads me to a question. So, do you know what happens if you take, let's say, PA or even true arithmetic for that matter? So, you can build sort of quote unquote generic sets, right? By taking true arithmetic, adding a new unary predicate, and then taking the Robinson generic for that. And do you know what happens with that in the case of arithmetic?
Well, I thought about it for like a minute because, so I mentioned it here because the only reason I thought about it for a minute is because when I was actually trying to write down, when I was actually trying to write down why CP generics have to be neutral, I kept running into certain obstacles in, I think it was like it was either like the pi 2 or the sigma 2 case. Eventually I cleared those, but it seemed when I reread some of those papers by Robinson, it seemed like there was a connection there because there was sort of somehow the theory that is actually preserved is well, it was sort of matching up with that, but then I didn't end up needing to go any deeper in that. So so my answer is no, but I don't know, Roman or Jim probably has thought about it at some point. So
I haven't. Jim, have you?
No, I don't.
okay. It might be worth thinking about. let me put that.
In the sort of quote unquote standard case where in this Chakas-Pillay situation, it turns out doing the Robinson forcing construction and doing what they do, it ends up being the same thing.
Yeah.
For simple reasons. But I was kind of curious because this case is so much more significantly different. I'm not sure I'd be curious to know what happens.
Yeah.
Okay.
Yeah, it's not obvious, but yeah. Let me just leave it at that. I haven't given it enough thought. It's probably worth looking into.
No, but that's all interesting, and there are all kinds of questions to consider. So, Athar, I certainly would like to see the draft when you have it ready for distribution, and perhaps few other people want to take a look at it too.
Sure. Yeah. I mean, just I'm happy to send it on, but it's not very different from what I've kicked around with you earlier. So
right. But always one has a feeling that perhaps the proof should be a little simpler.
It should be. Yes.
But maybe that's that. But if not, that's interesting too.
Yeah.
So I'd like to see that when you have it written up too.
Sure. I'll be happy to send it around.
Okay. Any more questions?
Yeah, maybe this is kind of a dumb, naive question, but just on the standard model, what are the CP generics? I mean, is there some sort of, obvious characterization of which subsets of omega are CP generic for the standard model?
Well, I think that this condition that you start with things that are not indefinable closures, you end up saying nothing. Saying your CP generic over a prime model says nothing.
Any set is generic.
Yeah.
Any set is generic. I see. Okay.
All right. So this is always true, right? I mean, this is never true. In other words.
Oh, this is never true. Oh, yeah,
true.
right. Yes, of course. Yeah. Oh, right. Yeah. Okay. Duh.
Because everything is in the definable closure of everything else. Right?
You have to be in a model that's big enough.
Yeah.
Okay. Yeah. Right.
Yeah. When I was working with this, it very quickly you end up realizing that you need saturation to do anything with. Yeah. If you want to talk about definable closures and in PA, at least you have Skolem functions, so you can sort of enumerate them in a type. So if you have saturation, you can do stuff, but it's not. If you're in a small model, there's not much you can say.
Oddly, we don't even actually have a good handle on what happens with these things in models of Pressburg arithmetic. I mean, this is still kind of a open question about how do you deal with this in Pressburger. I mean, even well below the level of PA, right. Like even the level of Pressburger, we don't really know what's going on.
I mean, yeah. Saying anything more than right? More than the ordering. Like once you, with the ordering, you can say something, right? That like every pattern that you want will show up, of something like that, right?
But look, but if you stop there, what kind of genericity is this?
Every pattern in the ordering, that sort of
every pattern to occur. Is this some notion of genericity that's of interest?
That'll be generic over just n less than.
Yeah.
Right.
Okay, that's sensible. And actually, it's an interesting fact that the theory for that actually works, and really, when the sort of full theory of generics works at that level.
Okay.
Sort of, because what you're really after for the CP stuff is a lot more than we're saying here.
Yeah.
Right. And so at the level of n less than, that sort of definition works, and everything you'd ever want works. But beyond that, we don't know what's going on.
Do we know anything about the theory of a model of PA with a CP generic? I mean, if the models are elementary equivalent, are the models with that expansion elementary equivalent or anything like this?
No. Well, we don't know. Let me say, the answer to your question, your first question, do we know, is no. What we know is essentially that we don't, like there's no sensible theory of neutrality with, so a model, a recursive saturated model and a neutral subset. And so if CP genericity implies a neutrality, which at least in the saturated case it does, that means that there's maybe no real no sensible theory that we can come up with. So yeah.
Thanks.
Okay. All right. So I'm happy to stop here if there's no more questions.
Okay, look, so no more questions, but this is work in progress, so maybe we'll get another talk in a month or two. But let's see what happens.
Then I'll be teaching, so probably not.
And I want to advertise, well, the talks that are coming will be all about Ramsey types of combinatorics. Leszek Kołodziejczyk from Warsaw will speak next week, and this is all about some recent work about the reverse mathematical status of the infinite Ramsey theorem for pairs. And so some joint work with Yokoyama and a few other people. So that should be interesting. So be there. And Leszek is a very good lecturer, but he needs to be interrupted and he needs to speak slower than he usually does. So it should be a good talk.
What time is that one out?
I don't know. This. I think, let's see, this is probably at 2. Let me see.